We learned on Friday that 200 years ago, or at least 198 years ago, a guy named Hans Christian Ørsted made a pretty important discovery. We said on Friday, in fact, that it is arguably the most important technological discovery ever, because just about every piece of technology that we use today is based on, at least in part, the idea that was discovered by Ørsted almost 200 years ago. And that idea is this: electricity generates magnetism. Simple as that. Electricity generates magnetism. If you have a moving electric charge, whether that electric charge is moving through the air or moving through a liquid or moving through a wire, if you have a moving electric charge, then it will generate a magnetic field. Simple as that. Now, what does that magnetic field look like? That magnetic field is going to be circular. The magnetic field surrounding the bar magnet, you remember, was looking like this. The magnetic field surrounding a moving electric charge will be a little bit easier to see and a little bit easier to predict because it's just going to be circular. This X is going to represent a charged particle going into the page for us. In fact, specifically, we're going to make it an electron, a negatively charged particle going into the page. The magnetic field surrounding that X, or surrounding that moving charged particle, is going to be circular. That's one field line. Here's a second field line. Here's a third field line. What do you notice about those three field lines? They're all circles. What do you notice about the spacing of them? Chase? Yeah, good. The space between them grows as it gets further away from the moving charge into the page, right? Space gets further and further away from each other. That means that the field strength is getting weaker and weaker and weaker, which should make sense, right? If it's the wire and the current in the wire that's causing the magnetic field here, then the strength of the magnetic field is going to weaken as you get further away from whatever it is that causes it. It's the same case with a magnet, right? You have a magnet, the further you get away from that magnet, the weaker the field strength is going to be. Now, how do we predict what the direction of this field is going to look like? We know that there's got to be a direction. Magnetic field, just like electric field, is a vector field. So what does the direction look like? Well, if it was just a plain bar magnet, then we would see that the magnetic field was going from north to south and looking something like this, right? What about this? We're going to use a new rule, a hand rule. We call it the wire grasp rule to predict the direction of the magnetic field there. Works like this. You're going to take, for a negative particle, your left hand. If it was a positive particle, you'd use your right hand. Take your left hand, because this is a negative particle, and you're going to stick your thumb in the direction of the moving charge. Which way is the charge moving in this example? Not towards us. It's pointing away from us, right? The X means into the page. Remember the analogy that I used, or the story that I told you guys about the dart coming towards me and away from me, right? As the dart is coming towards me, it looks like a dot. As it's going away from me, I see the feathers or the fins of the dart, and it looks kind of like an X. This is going away from me. So you're going to take your left hand, specifically your left thumb, and you're going to point it away from you, which I'm going to say is into the page. This is my page. Okay, my thumb is going to go into that page. Then I'm going to bend my fingers. It doesn't matter how much you bend your fingers. Bend them a little bit like this. Bend them a lot like this. Doesn't make any difference. Just bend your fingers and see which way they point. Thumb into the page. Fingers are bent. Fingers are bent a little bit here. You see my fingers? Which way are they pointing? You're looking at your fingertips, by the way. Okay, which way are my fingertips pointing? To the left. Oh, but wait, let's bend them a bit more. Which way are they pointing now? Nope. They're pointing down toward the bottom of the page, right? If I bend them even more, which way are they pointing? Towards the right. You can see that there's no conflict there. It just depends upon position. Above the moving charge, the magnetic field is pointing to the left. To the left of the moving charge, the magnetic field is pointing down towards the bottom of the page. And so on and so on and so on. So it just ends up completing a loop that ends up being counterclockwise. Same thing would be in the next field lines as well, right? We don't need to keep repeating that. Thumb in the direction of the moving charge, fingers bent however much you want in the direction of the magnetic field that's caused by that moving charge. Let's try one here with a dot. What does that dot mean? Coming towards us, out of the page. Okay, out of the page, coming towards us. Remember, we're picturing the dart that Derek threw coming towards me, and it looks like a dot, right? We're going to make it an electron again, so that means it's going to be my left hand. If it was a positive particle, like an alpha particle, we just make it a right hand rule, that's all. Okay, not a big deal. Magnetic field is circular, like this. Field lines are getting further apart the further you get away from this moving charge. You're going to stick your left thumb out of the page towards you guys, towards you. Bend your fingers. Oh, here they're pointing to the right, down, left. Look, you don't even have to do it in 3 or 4 places, right? Just do it in one place. Magnetic field is pointing to the right there. Well, then it's got to continue around in a loop like this. The magnetic field would be clockwise. Does that make sense? You don't need to draw this picture if you don't want, but you should write down this. To find the direction of the magnetic field, we're going to use the wire grasp rule. How does the wire grasp rule work? Well, we're going to stick our thumb in the direction of the moving charge. Now, if that moving charge is inside a wire, we would call that an electric current. So the direction of the moving charge or the direction of the electric current. My bent fingers, regardless of how much I bend them, my bent fingers are going to point in the direction of the magnetic field caused by the moving charge. You can see in the diagram exactly what we just did, right? Thumb in the direction of the moving charge. You can see here it's to the left, and then I'm going to bend my fingers around. It looks like my fingers are going in a loop like this. Let's do another couple quick examples here, okay? We've got an X and a dot again. X means what, Chibo? X means into the page. Yeah, it means into the page. We're going to make this a positive particle, okay? So let's make it an alpha particle, which has a charge of 2 plus. By the way, that 2 plus doesn't really matter for us in this question. We just need to know that it's a positive charge. But what does the 2 plus mean? What is the charge of an alpha particle? Yeah, Joshua? Okay, just answer my question first here. Yeah. Not 2 protons, but 2 times the elementary charge, which would be 3.2 times 10 to the minus 19. Yeah. Now, we don't need to know that here. We just need to know it's positive, right? How much positive doesn't really matter. Yeah, great, Joshua. What's your question? No, X means into the page. What does the magnetic field look like surrounding this alpha particle going into the page? Well, we're going to say it's a series of concentric circles here. Which way are the field lines going to point? Well, we're going to use our right hand for this one because it's an alpha particle. We're going to say thumb in the direction of the particle, which is into the page. And my fingers are going to point, looks like going to be clockwise here. Yep. Use your left hand if it's a negative particle, and use your right hand if it's a positive particle. So this is an alpha particle. We're going to use our right hand. The next one, Shiva, we're going to make a negative particle here. We'll make it an electron coming, what's that dot mean? Coming towards us or out of the page. I'm only going to draw one field line there just because I've kind of ran out of space. But you know that it's a series of circles, right? I'm only drawing the first one. Shiva, this one's going to be our left hand. Left hand is going to be pointing, left thumb, sorry, is going to be pointing out of the page. And my fingers are going to point clockwise again, right? How is that possible? How can I get an alpha particle pointing with a magnetic field clockwise and an electron with the magnetic field pointing clockwise? Yep. Yeah, yeah, they're going in opposite directions, right? So it's opposite charges of particles, which produce opposite fields, but then the opposite direction of the movement kind of cancels that out. We have a magnetic field pointing clockwise in both cases. Let's say this is a negative particle, an electron or electrons moving to the left. Maybe it's moving through a wire to the left. Maybe it's just moving through the air to the left. Doesn't really matter. Say thumb in the direction of the particle, which is, oh, we can't really say clockwise or counterclockwise there, right? Look at the board marker here. Okay, this is the movement of my electrons. We're going to say thumb, direction of the particle, fingers, direction of the field. If we follow that along with our other finger here, you can see that the field goes like this, right? This is the plane of my page, okay? Let's make this vertical, the plane of my page. I'm the page, okay? Physically, my body is the page here. Right now, where are my fingers right now? My fingertips, where are they? Don't tell me which way they're pointing. Just tell me where they are. They're above the wire, right? Which way are they pointing? Away from the page, out of the page. Now, when we're in front of the wire, we're in front of the moving charge, right here, which way is the magnetic field pointing? Down. Let's not say down, let's say toward the bottom of the page. Because if my page is vertical like this, toward the bottom of the page is down, right? But if your page is horizontal on your desk, then toward the bottom of the page is not down, right? Does that make sense? Our frame of reference is going to be the page. So we're going to say here the magnetic field is pointing toward the bottom of the page, into the page, and toward the top of the page. Now you can use your left hand and forget about kind of wrapping it around like this and just place your fingers in different positions. You can say thumb to the right, to the left. Fingers right now are above the wire, they're pointing out of the page. My fingertips right now are in front of the wire and they're pointing toward the bottom of the page. Below the wire, my fingertips are pointing into the page, and this is where it gets fun to watch you guys in unit tests. As everybody's quiet and you're trying to do hand rolls and you're contorting your body like this to try to get your fingers in behind there. Fingers in behind the wire, they're pointing toward the top of the page. So how do we draw this? Well, I'll tell you what, you don't even have to draw it. You can express it in words if you want. Out of the page, down toward the bottom of the page, into the page, toward the top of the page. Or we could say the magnetic field would be pointing above the wire. The magnetic field is out of the page, right? Shibo, dot means out of the page. Here the dot meant the electron was coming out of the page. Here the dot means the magnetic field is pointing out of the page. It's just a direction. Below the wire, the magnetic field is pointing into the page. In front of the wire, the magnetic field is pointing down the page. And behind the wire, the field was pointing toward the top of the page. See the notation I used there for in front and behind? I've just indicated in front of the wire or in front of the moving charge with a solid line, and it's a broken line to indicate in behind the wire there. Now, somebody asked a few minutes ago, left hand versus right hand. Good question, right? Left hand versus right hand. The rule is if it's a positive particle, use your right hand. If it's a negative particle, use your left hand. Now, there is a term here that we rarely see, but it does rear its head every once in a while. When we talk about electric current, we mean the flow of electrons, electron current. But every once in a while, we see this other term called conventional current. It would be the flow of positive charge. They don't use that term very often. Okay, if they're talking about the flow of positive charge, then they're usually then they're usually going to express that with a diagram, right? You can see in this diagram, first diagram over here, that we have the flow of positive charge. And we see the flow of negative charge right here. But if they say the word electron current, clearly it's the flow of electrons. If they say the words conventional current, then it's the flow of positive charge. If it's electron current, use your left hand. If it's conventional current, of course, it's positive particles, so use your right hand. All right? Don't see it very often. I can probably count on one hand over the years the number of times that I've seen it on a test or an exam, but it's happened. So we want to be ready for it just in case. I'm sorry? Yeah, it's the flow of positive charge, yeah. Now, I'm going to do another example here for you. We're going to have a wire horizontally like this with a conventional current going to the right. Now, strictly speaking, you can't really have positive particles moving in the wire, right? It's negative particles moving in the wire. But every once in a while, you see it expressed that way. I won't give you the history of why it's sometimes expressed that way, but the bottom line is it works out. Okay, it works out, even though that's not really the way current flows. It's really electron current. It works out. Bottom line is conventional current, use your right hand. Electron current, use your left hand. Well, because the electron current will be flowing left and conventional current will be flowing right, we'd end up with the same answer anyways, right? This is conventional current, though. That's the way it's expressed to me. So I'm going to use my right hand, assume positive flow, even if it doesn't really happen that way. Assume positive charge. Right hand, I'm going to stick my right thumb towards the right side of the page. My fingers right now are where? Don't tell me which way they're pointing. Where are they? They're above the wire, and they're pointing which way? Out of the page, away from me, or out of the page, right? They're pointing towards you, so out of the page. Okay. Right now, my fingers are in front of the wire, and they're pointing toward the bottom of the page. Right now, my fingers are below the wire, and they're pointing into the page. Right now, my fingers are behind the wire, and they're pointing toward the top of the page. So let's draw this out here. Above the wire, they're pointing out of the page. That's going to be a dot. Below the wire into the page, that's going to be an X. In front of the wire, it's toward the bottom of the page. That's going to be just a solid line. And behind the wire, they're pointing up the page. That's going to be a broken line like this. All right, I'd like you right now to work on worksheet number 10. There's 6 questions on this worksheet. It's going to go fairly quickly for us. We're going to work on the whole thing in class here and not take it home for homework. We'll give you about 10 minutes or so to do that. Just make sure that as I'm walking around, as you're struggling with any of this, ask me questions. If it's with a notation as to how to express something, that's fine. If it's whether you use your left hand or right hand, that's fine. If it's how do I know which way the field is moving, that's fine. Whatever questions you got to ask it. This is the kind of thing that once you get the hang of it, it tends to be pretty easy. But it sometimes takes a little while to get the hang of it. So if you're struggling a little bit, that's okay. Just ask the question. Taking a quick look at number 1 and 2 here. Number 1 says draw the magnetic field surrounding an electron current below. Electron current means it's negative particles. The X means it's going into the page. So we'd say thumb into the page. Fingers are going to go counterclockwise. Now there's multiple circles here, right? But if we're just trying to determine the direction, we only need to draw one of them. Number 2, draw the magnetic field surrounding the wire showing electron current below. We're going to use our left hand again. If it said conventional current, then we'd use our right hand, right? We wouldn't lose any sleep over the fact that, wait a second, how can protons move within a wire? We wouldn't lose any sleep over that. We just go directly to our right hand and use the right hand wire grasp rule. This is left hand though, because it's electron current. It's coming out of the page here. So we're going to say thumb out of the page. Fingers are going to go clockwise. Going to look like this. Let's take a look at the third one as well while we're at it here, and then we'll leave you with 4, 5, and 6 yourselves here. 3 says, Find the direction of the magnetic field surrounding the wire showing electron current, negative particles, pointing to the right. We'd say thumb to the right. Where are my fingers right now? Where are my fingers right now, Kristen? Not which way are they pointing, but where are they? Yep. Above the wire. Yep. And which way are they pointing, Hamish? Into the page. So above the wire, we'd say into the page. Hamish, you had a question? No? Okay. So below the wire, my fingers would be pointing out of the page. In front of the wire, my fingers would point towards the top of the page. Don't say up. Okay, right now, with my frame of reference, it's up. But with your horizontal page, it's not up, right? It's towards the top of the page. And behind the wire, my fingers are pointing towards the bottom of the page. So it would look like something like this with the notation that we're using. All right, let's finish up 4, 5, and 6, and then we'll take a look at those together as a group in just a couple minutes. All right, number 4 says, find the direction of the magnetic field surrounding the moving alpha particle. It says moving alpha particle, so we know that it's a positive particle, but we also know that it could say conventional current, okay, and therefore we do the same thing as we do in this question. Right hand, hey, we're going to stick our thumb in the direction of the particle, which is toward the top of the page. To the right of the particle, my fingers are pointing into the page. To the left, my fingers point out of the page. Behind this wire, my fingers point towards the... Which way? Towards the left, yeah. Behind the wire, they point towards the left. And in front of the wire, they're pointing towards the right. Notice, again, the notation that I'm using here. There's more than one notation. You could express this in words if you want instead of a notation like this. Okay, the notation that I'm using is when you see a break in the line, it means it's behind. Okay? So when you see a solid line, it's in front. When you see a break in the line, it's behind. Number 5, the diagram below shows the magnetic field surrounding a moving electron indicate the direction of motion of the electron. So this is kind of backwards, right? This is kind of like in physics 20 when we saw the equation V equals D over T, and we had to rearrange it to solve for D. Did a little bit of algebra on an equation. We rearranged an equation. Here, we're rearranging a hand rule, the wire grasp rule. Usually it's thumb, see which way your fingers point. This time it's fingers, see which way your thumb points. We know that it's a negative particle, so we're going to use our left hand, and we're going to forget about your thumb for a second. Just make your fingers point clockwise. When my fingers point clockwise, my thumb will automatically point out of the page. And finally, question number 6, this time we've got an alpha particle. We could have said conventional current. Yeah. We'll just do 6 right now. Alpha particle, positive particle, right hand, we're going to say, we don't know which way it's moving. That's what we're trying to find. But we do know that my fingers need to point clockwise. My right fingers need to point clockwise. Which way does my thumb automatically point if my fingers are pointing clockwise? The end of the page, so we would represent that by an X. One more rule here, used in a slightly different context. When we have a wire with a current going through it, it generates a magnetic field. If we wrap that wire up around in a coil that we call a solenoid, fancy word for a coil of wire, then that magnetic field will be magnified. Not because in any one section of the wire it's stronger, but because we have more sections of the wire kind of wrapping around upon themselves. You can see that this section of the wire would generate a magnetic field according to the wire grasp rule. So would this, so would this, so would this, this, and this. All of those sections or all of those loops of wire would each generate a magnetic field according to the wire grasp rule. But because they're looped around like that, the magnetic field caused by each section kind of multiplies. Now, you can see inside this coil or inside this solenoid, we have what we call a core. We don't have to have a core there, but if we have a core that is ferromagnetic, you don't have to draw this diagram if you don't want to, because I'm going to explain the rule in just a second. If we have a core that's ferromagnetic, then it'll maintain the effect better. right? Because what happens is the magnetic field caused by the wire magnetizes the ferromagnetic material, which makes this ferromagnetic material. The nail that you wrap the wire around, it makes it into an electromagnet. We get the same effect even if we don't have the core, but it just seems to be magnified a bit. At least it stores longer if we have the ferromagnetic material in the middle of this core. All right, so we're going to learn a new rule right now that's used to find the polarity of this coil. We could find the direction of the magnetic field around one particular section of wire using the wire grasp rule, but there's an easier way to deal with this, and that is using this new rule that we call the coil rule for solenoids. But it's going to be a little bit confusing at first because it's exactly opposite to the wire grasp rule. Remember the wire grasp rule? Thumb was direction of the moving charge, fingers was direction of the magnetic field. This time, the thumb is in the direction of the magnetic field. We're going to say the direction of the magnetic field inside the solenoid or inside the coil. That's important, and you're going to see why that's important later on, that word inside. The bent fingers are going to point in the direction of the moving charge or the direction of the electric current. So remember, wire grasp rule, thumb moving charge, fingers magnetic field. Coil rule, thumb magnetic field, fingers moving charge. Yep. Yes. Yeah, the movement is exactly the same. You got to bend your fingers in the same way, right, Hannah? It's just that we're swapping the terms there, reversing them, and you're going to see what I mean by that in a second. All right, I just handed out scrap paper to everybody. Everybody should have a piece now. What I'd like you to do with that scrap paper is make it a little manipulative, like a kindergartner grade 1 manipulative, to help us to use another hand rule, the coil rule, to find the polarity of this solenoid, the polarity, the north-south end of this solenoid or what's become an electromagnet. So here's what I want you to do with that paper. I want you to roll it up like this. You can put a piece of tape on it if you want. There's Scotch tape up here. You can run up here, grab a piece of Scotch tape and tape it up if you want, or you can just hold it like that. I also want you to do the following, and this may seem silly, but trust me, if you don't do this, then many of you will end up getting mixed up. Please, on one side of it, write the word front, and on the other side of it, when you flip it around, write the word back. Front and back. All right, let's do an example here now of this coil rule thing. I'm going to draw a picture with a core. Remember what I said, you don't actually need a core inside, but it's better if you have this core inside. This core you want to be a ferromagnetic material like iron or steel or cobalt or nickel or something like that. I'm going to draw some wire going around that core. Can you see what I've done here? My wire is going around it such that you can see the wire that's in the front of the core, and then you can see the wire kind of looping around and behind the core. That makes sense? We're going to attach that to a battery. The battery is going to look like this, with a positive terminal and a negative terminal. That's always the way a battery would look, by the way. The positive terminal is the long end, the negative terminal is the short end. That means the electric current will go this way. It leaves the negative end, and it goes back towards the positive end. Okay, there's nothing magnetic about this. Okay, this is just electrically, okay, this is the negative end of the battery, this is which way the current goes. You can see though, it's going to go up in the back and then down in the front, up in the back, down in the front, up in the back, down in the front, and it's going to loop around back to the battery here. Okay, just pure question right now. We haven't done anything with the answer here. We've just identified what the question is telling us. The electric current is going counterclockwise here, up in the back, down in the front. Now, take the manipulative that you just made, this coil of wire, or this wrapped up piece of paper, and I want you to look at the word front. Okay, I'm looking at the word back, but only so that you can be looking at the front of mine, okay? So that it's the same perspective from mine as it is from yours. Now, which way is the current going in the back, in the front? Downwards, right? Remember we said for this rule, we're going to stick our fingers in the direction of the current. Bent fingers move in the direction or point in the direction of the moving charge of the current. So we're going to stick our fingers right on the word front. My fingertips right on the word front, pointing downwards. And then you're going to bend them. So my fingers, the direction of the moving charge, the direction of the electric current is down in the front. You can see that in the picture there. So I'm going to put my fingers down in the front. Which way does my thumb automatically point? To the left. So the magnetic field inside the coil is pointing to the left. That means this will be a north pole and this will be a south pole. Wait a sec, didn't we say magnetic field points from north to south? Magnetic field points from north to south outside of a magnet. Inside it points from south to north. If we extended that around, we don't need to, but if we did, it would go from north to south outside. Let's try another one here. Once again, I'm going to draw a core, although we don't really need it. Well, it makes it a little bit simpler for the diagram, but it also makes it more effective for the magnetic effect. Wait a second, isn't this the exact same diagram? This is the positive terminal of the battery, negative terminal of the battery. Electrons go around this way. But wait a sec, now the current is going up in the front and then down in the back. Up in the front, down in the back, like this. Make sense? All right, take your manipulative. Look at the word front. Look at the word front. Point your fingers up in the front. Bend your fingers around. Okay, make sure your fingers are still pointing up in the front. Everybody do this, okay? Everybody do this. When I point my fingers up in the front, my thumb will automatically point this way, which means this is south and this is north. Now, if these two diagrams that we drew are actually two separate scenarios close enough together to interact, what's going to happen? They're going to repel each other because we get south against south, right? Let's do another one. Here's our core, and let's make our wire wrapped around like this. Here's my battery. What's this, positive or negative? Positive. This is negative. Electrons are going to go this way, to the right in the front, and then to the left in the back. Going to go around like this, clockwise. Now, I want you to make your coil, this piece of paper that you wrapped around and turned into your solenoid, your coil of wire. I want you to look at the word front just like this. I want you to stick your fingers on the word front pointing to the right. And I want you to bend your fingers around, bend your hand around. And which way does my thumb automatically point? Down. So we're going to say the magnetic field is downwards inside the coil, which means this is south and this is north. One more, and then we're going to wrap it up for the day here. This time, we're going to have a similar setup here. We're going to have a battery over here, but I'm not going to show you which way the battery goes. I'm not going to show you which is positive, which is negative. Rather, I'm going to tell you that this is the north end of the electromagnet that's just been made. This is the south end. So we're going to work backwards. North and south. We know the magnetic field inside the coil goes which way? It's from south to north, right? Up. So instead of saying fingers current, thumb field, we're going to say thumb field, which is up. My fingers in the front automatically point to the left. So I'm going to say my electric current is to the left in the front. And to the right in the back. That means that the electrons are going this way. That means that this is the negative terminal and this is the positive terminal. So it's going to look like this. Sorry, not two positives. That should be negative, right? Negative and positive, right?